Welcome, everybody. It's my pleasure to welcome you to this seminar. My name is Alex Bayan. I'm with the Intelligent Infrastructure Clusters here at CITRIS. I want to say hello to our web viewers. If you're watching this seminar online, you can IM us your questions, and they will be read to the speaker at the end of the talk. There's a two-talk announcement to make. Merlin Walker from UC Santa Cruz is going to talk about affective language in social technologies, and that will be tomorrow. And we have also William Cummings coming as part of the CITRIS Distinguished Lectures on Intelligent Infrastructure Systems come on Friday, and he's going to talk about intelligent design and implementation of nuclear power for carbon-free energy. So this lecture is co-sponsored by the iSchool and the Civil and Environmental Engineering Department in the college. And thus, I'm going to leave the Dean of the iSchool, Professor Arnaud Saxenian, do the introductions for the speaker today.
Thank you, Alex. It's really a great pleasure to introduce Henry Tirri. He's been a long-time friend both of the School of Information and of the College of Engineering. For those of you who don't know him, Henry is a Senior Vice President and head of the Nokia Research Center and responsible for Nokia's long-term research at the NRC labs and units worldwide. He joined Nokia in 2004. Prior to that, he was a tenured professor in computer science at the University of Helsinki. He's also adjunct professor at a couple of different universities in Helsinki. He graduated from the Helsingin Suomalainen Yhteisskola. In Helsinki, it's a unique school, he told me, but there's no English translation. And he received his BS, MS, and PhD in computer science from the University of Helsinki. I'm just going to say a few words about his publication activities. Henry has published more than 175 international publications in books, journals, and conferences in the areas of probabilistic and information theoretic modeling, text and data mining, neural networks, case-based reasoning, transaction processing, intelligent learning environments, knowledge-based systems, and data analysis in education. His work is both theoretical and applied in nature, and the applied work is strongly multidisciplinary, which of course we like here. Recently, he's been interested in applying his modeling methods to information retrieval, including internet search engines and wireless sensor networks. And I think what he'll talk about today, it says here in his bio that he's excited currently about, is the possibility of developing applications and services that don't scale down, but rather allow millions of computing devices to interact and implement very large-scale services depending on contextual data. With that, I would like to turn it over to Henry.
Okay, thank you. And I guess I'm supposed to say hi for all of those people who decided also to look at this a little bit late spring rain that we have here in the Bay Area. So I can say this already because next year is going to be 10th year that I've spent at least half of the year in the Bay Area, also in my former life. I originally came here in '98 to NASA to work on the 2003 Mars rover mission. So that was the origin of my sort of affiliation here. Today what I'm going to do is I'm going to talk about things that I'm deeply interested in, but also to understand why I'm deeply interested in that, I need to both borrow from my great colleagues at Nokia Research, some of the work that we've been doing, and also indicating the directions that we do, directions of the research that we do there. Also, at the same time, to explain why I'm personally interested in this type of a topic. I'm a computer scientist by training, married to education, meaning my wife is a professor in education. And like Anna was mentioning, I've done a lot of multidisciplinary work as modeling allows you to do that type of things. So you can view this as a person who is interested in modeling, but it's a deep hacker. It's going to be my 38th year next year of hacking computers, starting from whistling to the phones, to get free long-distance calls. And so basically, it's a really combination of all these different things. And also, to add to that mix, I wanted to be a biologist, but I ended up being here. So anyway, like I said, I want to just acknowledge that many of the things that you see here empirically come from different parts of Nokia Research Center. Nokia Research Center is a misnomer because it's not any single place anymore on Earth, but it is different labs worldwide from Beijing to West Coast. But the name has stayed more than 20 years now. The first question that I've always been asked is it's usually a two-part question. And that two-part question comes in, why did you go to industry? I was a 10-year professor, many, many years in academia. And the second question that I've been quite frequently asked, that why go to Nokia now? I mean, considering especially here in the Valley and all the challenges that you can see that companies like Nokia and many others are facing on this one. And the answer to those two questions are also related to today's topic. To answer the first question, my career planning has never been very good. And so I basically was just sort of, it's a sequence of random accidents. Also, what Anna was mentioning, I joined Nokia 2004 as a research fellow with a deliberate request that nobody would be reporting to me and I would be just doing, research. You see how well this works out. So, but the second thing is that I also had done a lot of work in my life and in academia and wanted to make impact first as an individual researcher, then having a research team, then having a research lab, about 25, 30 sort of PhD students plus then postdocs. But I really wanted to find a way of touching people's lives. And when this opportunity came up and I was very interested in looking at, particularly my passion was already seeing the billions of devices, computing devices as a computer scientist that are prevailing on Earth. To utilize this somehow, Nokia is a great place to be. And that's one of the reasons. Second reason, which is a question of, there is never a better time to be in industrial research, an industrial research lab, when there's uncertainty of the future, turbulence. Nobody can be arrogant because nobody knows where the future goes. And as you can see, the playing ground is a rather mixed one. So like Rick Rashid and Prit Banerjee and I, when we have these chats here in the Valley of all the having and saving the world, we all point out that this is a great time to be leading research. Today I'm specifically interested in energy, distributed computing, combined with communications. And I just want to point out how prevalent certain things start to be nowadays. And okay, this is a typical thing which shows beautifully on a laptop screen and the numbers done so well on the big screen. But this is just like showing the social networking structures that we have globally as we look at the thing from here, from North America, then to Far East. And you can easily see that you have these things like total internet, China 205 million, social networking 95 million. Interestingly, the largest one is actually the Baidu, 42 million. And then total APAC, for example, total internet, 462 million users. So we can at least say that we have an communication infrastructure that has never existed before. And there's no clear prediction currently where this will saturate. That's the first observation. The second observation is that, as we know well, there is no other pervasive computing technology like what you call here cellular phones and tend to be called mobile phones or handset, and which as I'm a computer scientist, I always view these as mobile computers, regardless of what type of capabilities these devices have. Of course, the high ends are nowadays obviously already mobile computers. So the pervasiveness of this technology is really changing lives. And this I can witness from what I see. This I can witness what I see from the work we do in research, but also in the visits when I'm visiting Far East, India, Greater China, and these different areas. It's changing education, it's changing medicine, health, very important areas in the world. There's always this favorite, saying that I shamelessly quote. It's good to steal very good ideas. Something which is called Linus and Henry Law, which is that what makes people to adopt new technology. And the first one is survival. second one is social relationships, and third one is entertainment. And then the business comes somewhere in the hierarchy much later. And, but in my world now, currently what one can see is what are the drivers of these hugely interesting global application areas that we are looking at. They are clearly health, education, and then some kind of, I don't have a good name for that. I tend to call these aggregate services where traffic is and complex systems monitoring that. And of course, looking at the current situation of ever-increasing variance in the natural disasters, also environmental monitoring by the end of the day. Anyway, like I said, the world has become very flat. And this flatness comes from the fact that the wireless communication technologies have enabled an increase faster than people predicted, and also caused now a tremendous pressure to go on and increase things and building these more and more complex systems. Also with, unfortunately, the more and more requirement on the energy consumption. There's no road back. I mean, these things are so essential to these people that there's not an easy way of rolling and saying, hey, we're going to turn off the switch and you will be there. And just to point out, this doesn't show well, but the tiny white dots are representing the electricity, the grid on Earth. That's the internet access on Earth, and that's the mobile access in the world. And this is, in fact, somewhat outdated. So, because I've shown this same slide 2 years, and I'm sure this has changed. But basically, it just shows the interesting factors that we have where the power grid is. We can already access internet much wider than where our sort of fixed power grid is, but we can also then have communication access which is much wider than the internet. Why is that? That's because there is a humongous 2 billion people that do not have data connection in the network, but they do have a cellular network connection. So, it's easy to ignore the energy here, except maybe this one day in Palo Alto area when we had some planes flying somewhere which they should not be, and then people fast realized how important it is, again, to tap to energy sources. But if you go to India, if you go to Africa, if you go to the rural areas, even in China, the question of energy and charging and sort of energy efficiency is something that you live with every day. And in this communication technology, there's something very weird happening. It is a technology where people get very fast attached to a real-time communication, real-time interaction. And any disruption on that real-time interruption is, very disruptive after a while for people who are starting to rely on it. So there's all sort of different solutions on the energy sources. There's questions about how to build better energy battery life to devices and so on. But that's not so much what I'm interested in talking today. I'm more interested in talking about what can we understand about the energy consumption in communications globally in this hugely wide complex system that has billions of computing devices all around the world. The question is why I'm talking about this now. Why is now the time? I mean, energy questions have been there every, possible decade of introduction of new devices and that. So I just always look at the history. Remember I was saying about something about my hacking. So when I started hacking, there were all sort of interesting things like the Burroughs machine, which was the first mainframe that I hacked, Univac, and so on. And then later on, you could see that there's some kind of consolidation, and only very few of these remained. And there's also a shift on what becomes commodized and what becomes valuable. So I skipped the mini computer era here, which could show the similar thing. But if you go and look at the desktop evolution of the computer, I also do remember Apple IIs and Commodores and Sinclairs and even IMSI and all sort of weird stuff that is sort of slowly migrating. somewhere. And now we are living in an era where you can see Nokia, Samsungs, LGs, Apples, Dells, all these different devices, computing devices coming again. But by the end of the day, history has always shown that something like this consolidation will happen. Why this is important? Why is it important that this type of behavior is sort of relevant to today's discussion is the following. That consolidation comes together with the platform, and the platform enables a uniform access to a larger number of devices and sensors. And if that platform wouldn't exist, then you would have everything very fragmented as it used to be. So programming Baroque's machine was very different from programming UNIVAC. It was very different from CDC and so on. And so basically, that's one of the observations, that we are now living in an era where we see the history repeating itself again with these computers. But also every generation of computers has a very particular nature of being different. And what is different in this computer generation is that it's by default a communication device. It has inherently radio capability because of the first application for these computers, which was the voice, and then sending text messaging, which was, by the way, of course, accidental, also originally intended to a totally different purpose than it became. It's also an inherently first generation of computers that is very prone of getting different sensors in it. And I always wanted to point out that every time you add one sensor to a device of this generation, meaning these handsets, you will change how people view something. So when you added camera, you changed how people are recording live. When you added GPS, it's changing how people are navigating. Because of the sheer volume of these sensors that we add there. Notice, by the way, that for me, camera, microphone, GPS are sensors as the same way like it would be chemical sensors, accelerometers, or many other things that you have in fact, the whole radio itself is a sensor. So a device, a modern device that you're probably carrying with you, especially if it's so-called global, I guess nowadays most of the high-end devices are global communication company, has 12 radios in it. So it's a very, 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 very multi-radio already. The interesting, another thing with this, which makes it now relevant for the sensing part, is that it's not only a mobile computer. I could argue that my laptops were mobile. I could carry them around. But it's something that we used to carry and have an attachment to, so we carry it with us. So it's much better than just being mobile. It somehow becomes a sensor which is related to the environment where you always happen to be. And that's important because you can imagine, for example, that you do a sensor network, that you do a grid, which is uniform grid around North America, but that would have as many nodes then in Montana, which is, by the way, as a sort of geographical education, is the size of Finland in area. So Finland is pretty much like Montana. But we also do have the similar areas than Montana that have very little people. So the question is that why do you put the grid there if there's no particular, nothing particular to sense? So that's another interesting thing. You are in the areas where the people are concentrated, you can sense. Also, the computational power, as we know, still follows Moore's law. But now suddenly this generation of computers connected to each other and connected to the backbone is suddenly ruled by different type of trade-off than we used to have. When I was a CS 101 major, we talked a lot about the memory and computing trade-off, or input-output and computing trade-off. In this wireless world, in fact, the transmission, energy, and computation trade-off is as fundamental as it is. Why we don't talk too much about it yet? It's because we've been restricted currently still with some other things, like the bandwidth or some economical reasons of doing things. But we are very fast approaching that particular trade-off limit. And like any other computer generation, we have at least 1 to 2 order of magnitude more of these than before. people quite frequently ask about the computational power of these devices. And of course, you can do a lot of calculations and nitpicking on this one. But approximately, if you remember that IBM Deep Blue, the guy, the sort of highly celebrated computer that was beating Kasparov in chess, is essentially the same computational power than if you would do a parallel processing with 11,000 N97s, which is one of the high-end smartphones, and so on. So we are also globally, if you have a concert in stadium with 40,000 or 50,000 of these devices, you have a former supercomputer power already in computing. Now, a lot of what I've been talking about, it's easy to understand that there's a high energy requirement by the new fancy things that these high-end mobile computers do. High-end mobile computers meaning that they are high-end devices with a lot of memory and a lot of different applications that you use here. So you might think that this is mainly a problem of AT&T and Manhattan and then in the Valley, by the way, which are the two other places that, in my experience, have the highest number of dropped calls. I hope there's not too many AT&T representatives in this room, but it's really bad. And that particular phenomenon comes, of course, from the bad prediction of the capacity of the networks with the very fast increased different type of use of the mobile computers, from the voice, text, to image download, streaming, and browsing. But let's look at the scale that I'm talking about for 90 seconds. So for that, I'm just going to play a 90-second video. So the point here is not, notice these are the Nokia numbers because it's easier for me to do the Nokia number calculation, and you can then multiply it with knowing that approximately we are about 40% of the share of the world, so these numbers are much bigger. So essentially what we are talking about here is the world's largest distribution and sensing platform. And this power of this platform is really amazing. I really like the phrasing that Anna was mentioning that I used in some of the keynotes a couple of years ago. It's really nice to be interested in systems that don't scale down. Right? By that I mean that many of the phenomena that you look at don't make any sense unless you pass a certain type of sort of quantitative limit. This is nothing new. I mean, most of the orthodox statistics says that certain tests are not valid unless you have a sample size which is large enough for that. We know that much of the analysis of correlational analysis of document doesn't make any sense unless you have 10 million to 100 million documents at least to do that. Sort of co-occurrences start being meaningful. But it's quite interesting also that it applies to this type of sensing. And then good examples are, of course, even the work that we've done here together with Berkeley at the NRC Palo Alto lab on traffic. So the traffic, which by the way helped me today of picking a right route from Palo Alto to Berkeley. So I'm very proud that I did my own record of driving from Page Mill Road to meet Anno, and I was I left at 5 after 11, and I was here, I think about 10 to 12, 10 after 12 or something like that in Anno's office. And that was because I checked from the traffic, Navtec traffic, that 94 is good. Bay Bridge was totally red, and even 8080 that tends to be pretty bad on that one was free, so I chose the route based on that. So one of the interesting and most obvious things to apply sensing is traffic. Notice that one should not look at traffic only as a very simple, simplistic way of looking at a traffic density on the map, but also as all the possible services you can build on top of the traffic to make it happen. So that you get early warning, hey, Anno is waiting you there, the traffic is very bad, you better leave now, type of things. The interesting part for me is that traffic was our first step, what we wanted to do. To do the similar thing, in the traffic we used the GPS sensor on the mobile devices to estimate the traffic density on the roads based on traffic models. As we know, if you have a very good model, parametric model to estimate the parameters, you only need a very small portion of the actual sort of population to do that. Now, going forward, we can do the same thing now for various different types of things. You can track the influenza outbreaks to a block level. In fact, this is some of the work that we are already looking at NRC Eurolab there together with the World Health Organization. You can do real-time weather monitoring, which is in fact quite interesting because if you think about when I was at NASA, I learned that there are 186 microclimates between Sausalito and San Jose. There's this beautiful map there. And everybody who's driving 280 down knows, from San Francisco knows some of these changes. So the interesting question is whether you can move to this microcell type of weather prediction on that. But also, for me, the fascinating thing in this global sensing is that you can do connections to latent things in a way that you would never believe would be possible. For example, people in California are particularly good at driving very differently when it rains than when it's dry. So looking at, in fact, the traffic behavior and connecting it to weather, you can do a very good prediction of what the weather is in a particular area, but based on how people drive. If you do this sensing and change the car to be a sensor, you can do much better. Changing a car to be a sensor means that you tap your wireless mobile computer to the sensors in the car. So you can, for example, know that your windshield wipers are on, so which is most likely it is raining when multiple sort of instances can be seen. But more interestingly, in areas where you have much worse weather than unless you go to Lake Tahoe here, is the black ice. And in fact, the sensors in the car tires that can look at the difference of the rotation can detect that, broadcast that to the cars in the same area, and you have a real-time detection of the black ice. Then there are totally different types of sensing that are not so much of measurement sensing. Like if you have a major events like earthquakes or some kind of other catastrophe, we already know how much you can do this citizen sort of reporting and sensing and building in that, which is very beneficial if you think about what's the information you get from a electrical box that tells you that yes, there was an earthquake of this magnitude, but you don't see the damage. But if you can have the picture of the damage broadcasted, it allows you to do a lot of things. Of course, IT is now a good example of where this was sort of, again, shown easily. I can't avoid telling you this one thing which I'm so proud of now. I donated some handsets to IT after the earthquake to re-bridge the schooling system so that they can attract the kids back to school to get the connections, and then they have the satellite networks, and some of it was donated by Google, and others. But I didn't know that there exists an organization that I now proudly belong to, which is Geeks Without Borders. So I love that one. So kidding. Okay, so this what I show now in the traffic. It's of course traffic is a problem anywhere. You go to Cairo, you go to Beijing, or you go to LA, or you go to Paris or whatever. But I promised you that there was a passion why I joined Nokia, and one of the passions is the developing economy. So why developing economies? Because the scale is so remarkable, because the impact you can make is so interesting, and thirdly, because it's still a place where the changes can be seen much faster than they can see in a sort of rich environment like we have in developed world. You just have to remember that there's no 3G in a lot of these places. SMS is the only thing you can do. And also the mobile computers there tend to be much simpler, look pretty familiar maybe, but much simpler than the ones that you have been now used to, but they're very pervasive. So the interesting question is that what do you do in sensing on an environment where your infrastructure suddenly allows a different type of communication that's going on? And we are currently working in India, for example, on this, bringing complex services with simple devices, even doing navigation, which is in fact a very different types of navigation than you use with GPS. It is in fact a landmark-based navigation by GPS phone, by sort of crowdsourcing, as the term goes, that people are recording and building this and triggering then automatic messages and going there. So that's an interesting new sort of domain. So these are the domains I'm interested in looking at this energy. The question of energy comes from like I said, as a computer scientist, I still carry a deep sort of interest in the fundamentals of computing. And originally when I studied computer science, the fundamentals of computing was really the theory of complexity. And then the complexity was in the memory. Complexity was in the computation. And then later on, something which was called the communication complexity, but never sort of became as fundamental or was taken into account. Nowadays, we know that there's another complexity that rules here, and it's the energy complexity of things. And this simply means that certain things are worthwhile doing different ways based on the ways that we understand how the energy consumption and energy is needed. Now I said something which is actually not true. We do not understand how the energy is consumed. We have surprisingly little understanding of system-level energy consumption whatsoever. And we can only have this niche information because there was a very, very narrow application area of digital voice delivery, and then a short message delivery. And then everything was optimized based on that one. Why this is interesting? Why do these wireless computers are so specific for this energy? Why I'm talking about, yes, of course, the big, centers need energy and all that. That's because if you do an empirical measurement, and that's a different thing than from the Shannon limit, is that the wireless transmission currently in a single bit can be over 1,000 times greater than a single 32-bit computation. This is remarkable difference. So, for example, in compression, this has a direct impact on how do you compress things and how do you send things to another. And this is some bar charts of showing where the energy is consumed on that. But it's interesting that also the technologies themselves bring a different type of energy. So the energy distribution, the used energy in 2G, so-called second generation that is mostly still prevalent definitely in the developing countries, but in a lot of places all over the world, and 3G users is already different. So notice that these are profiling of actual users using the network and doesn't explain yet why this is happening. And you could say some trivial things like different type of applications. But notice that, for example, the peaking of the 3G versus the much more sort of broader spectrum usage, energy spectrum usage on 2G. Another interesting aspect is that what is the difference on the energy usage of these new usage patterns. And now I'm talking about in this higher end devices where you can use application and messaging. So here it says like 18% of the energy usage goes for messaging. But there's another application which is, by the way, because of the measuring techniques not identified here, which is using about 30% or more of the energy. And then you have these very tiny things that are using energy. This type of measurement of the device energy usage on application level is very recent. These are the results that are done at NRC Helsinki in our energy group. And my first assumption was when I challenged this team was that go and find out, from the academia, where we are on that. And they came back to me and said, Henry, you can't find any of these things. And there are all these guys that are talking about theoretically the energy limits, but nobody has sort of measured truly the application patterns. And no, come on, guys, you just didn't go in the right schools. And then I went myself online and I did a real study on this one. And then I realized that, yes, this is true. There are a lot of good theoretical models of a very simplified nature, but they don't match at all the current usage of the mobile computers. And they tend to be also, if they are empirical studies, they are very, very small studies. So there are all interesting things now you can look at, like the energy distribution in different cell IDs. So where on Earth are you using this energy as a user? So again, the calls don't use that much energy necessarily. So the interesting question is that you're using applications in a very different way in different cells in the world. Or you can do these energy mappings. Like this is the different times of the day. The upper one is for the same population in, let's say, early wee hours of the day. And the latter one in between is, then a late afternoon. And there's a lot of phases in between. And the red means that it's, there's more energy usage. You see that these energy patterns of the users, this is an aggregate. This is not a single user. This is an aggregate of 100 people, are moving. And the energy consumption patterns are so distinctive that you can do even latent modeling of people's behavior. For example, you can easily figure out where they work based on this energy consumption alone. A more interesting question is cloud versus device. Remember that I was saying that the whole architecture of the back end to the device is, in fact, defined by this energy. So there are two easy examples of doing. If you download something, assume there's a browser running, and you are opening a file and looking at these pages of this, sort of artificial but synthetic text, and the energy consumption if you open it on a device. And you see certain differences, whether you do only the rendering or whether you just do the traffic and so on. So you can do measurements like this. Why I'm interested in this assessment is related with the sensors. One of the things that I've learned in energy is that it's very difficult to assess the true energy consumption on various different things. A lot of the models are based on assumptions. First time ever, now we have measurement devices that we can measure a lot of dynamic or large-scale system energy consumption. So we can look at how much, when we do some twisting, we spend on energy in the transfer side, which is this turquoise one, versus the sort of yellowish, greenish thing there, based on different solution. Whether you have the viewer, whether you're rendering only on the device, whether you do the processing at the back end, or whether you do it and you send the data and then you do the construction on the device. So the balance between the so-called cloud and the sensors, the complex sensors and devices, is like I always argue, by the end of the day, it's defined by this type of energy consumption. Now I'm going to, because in the interest of time and I want to leave a couple of minutes time for questions, I just want to add to this complexity a little bit more. So if you go to nanoscale, we know that we can actually do energy efficient computing per se by arranging our computing in a particular way. So I challenged some of the colleagues that I have of looking at how would we do this reversible computing now in real physical quantum computer together with a company that has that, together with the nanoscience people in Cambridge, to look at the particular pattern recognition problem in augmented reality, where you need to do a lot of different type of pattern recognition. We all know that Google wants to do something similar for the clustering. So again, the interest here is that the reversible computing, as we know, if you approach this logically reversible computation, your thermal dissipation goes down, and fundamentally you use less energy. So now when we are looking at the computations in the material, we can also reduce some of the energy on the device. And the real question becomes that what sort of, this VNL is a von Neumann-Landauer bound, meaning that what sort of energies we are using, the same way like we're talking about the energy that is needed to do certain type of communication based on the Shannon bounds. So my point here is that we are such an elementary stage currently on this one that we are barely starting to do the assessment, but the needed sort of energy understanding will be fundamental of building those services in the developing countries, services like the traffic and others in the developed countries. They will be fundamental how we arrange our computer infrastructure globally. And by the end of the day, also, can we move to very energy efficient sensors that are based on different type of computing principles. So it's a good stack, like we say in communication, and there's interesting challenges there. So this is what I wanted to say today, and I hope you have still some time for some questions.
We'll have time for some questions from the audience.
This is a question about onboard sensors. So sensors on the human body have a principal limitation, and that it's similar for all sensors, really, and that's power, or the stored energy, and how to manage that. So my cell phones, notice plural, are necessary because I can't have enough power, energy, in one cell phone to last for navigation and simple calling in a 12-hour period. I can't run a sensor on the body without some really smart duty cycle management. So could you comment on the power to the sensors?
Oh yeah, I mean, the whole point on the energy question is this. I forgot to mention that the battery technology, unless there's some disruption, seems to be going up like 5% annually, which is what we see now. I always point out 6150. Notice, by the way, this is way beyond I was at Nokia. I was using 6150 Nokia handset that easily lasted 1 week with me. So I sort of, charge it every weekend or so. That partly because of the usage patterns and the type of applications we currently are doing in these mobile computers has progressed much faster than our understanding of the energy consumption on the system level, and both in the programming and both also on the sort of technology, whether we talk about the battery technology or the computing technology. And that mismatch is getting worse all the time. And that's the reason you see so lousy, usage times on any of the mobile computers. Now, when you go to the sensors that are body sensors or sensing biological processes or others, you have to separate two different things. How much energy you need in that sensor to store and broadcast that information, and then how much it's needed to sort of stay awake or how would I say, stay alive. And one of the observations that we already are, in a, again, very crude sense have done is that the sensors themselves, if they need to broadcast only a very short distance, as we know some sort of radio broadcasting energy calculations, they need very little energy to do that. So it's very beneficial to have mobile sensors like handsets to move around and detect the other sensors' information and collect it, because it's still, the handset still has so much more power than those biological sensors. So the biological sensors or other type of electrical implantable sensors don't need to have that much energy. Of course, you can charge them by movement, and you can do various different types of inductive charging and others. But the real question there is that if you keep standalone sensors and spread them around the world, the problem is that you can't do very much with these small sensors because you can't get the energy to last. If you let them just to communicate a short distance, but to a higher energy power sort of collector, like a handset is not a sensor itself anymore, but it's a collector of other sensors. And that makes it very powerful. Because remember, I said the handsets are there where you are. So it collects from that environment. But sensor technology is also developing all the time. I didn't talk at all of the questions of the different types of sensors that one has. But it's easy to see that it's not so simple to do a very long-lasting sensor unless they are chargeable by movement or if they are in nature by some kind of a nature process, solar energy or something else.
Glad to see you back at Berkeley. Two-part question on energy. First, are you measuring both the infrastructure energy and the device energy, or just the devices? And how does that vary depending on whether devices are in use? I know infrastructure tends to use about the same power whether anybody's making any calls or not.
No, actually it isn't. The infrastructure tends to be using you can do intelligent base stations that are sort of waking up on that. Infrastructure energy, we know well from the cloud already the energy problems that anybody has in the heat dissipation, which means that you are wasting a lot of energy. What interests me in the infrastructure energy is this Lucent Bell Labs type of a green initiative that you try to push down the communication energy needed to do the backbone communications multiple order of magnitudes by creating better codecs. In my world, this means that you don't need to push so much energy to that because your distinction between the signal and noise is much better and you get closer to the Shannon limit. But basically, infrastructure and the device balance is a very interesting one, and I'm not sure which one will fall apart first. It might well be that the infrastructure also will fall apart much faster. What fascinates me is this balance. Can I somehow, when I'm introducing a new device, I'm introducing a new energy source still. And in a centralized infrastructure, the challenge is that I just add more load to that network, and the network has to be updated based on that. And that balance is an interesting one. I have I guess I'm being currently so fascinated of looking at just the transmission balance, and currently I'm thinking that the cloud data centers and that energy consumption, there's already a lot of activity of looking at that because it's a necessity. We are already reaching that bound. But still, the real good question is that I always pose is, how complex multi-billion sensor service can we maintain on Earth with the energy that we can have? And that would count the infrastructure together with the devices. So, I mean, there is a limited amount of energy burst we can do at any given point of time without becoming a sun, I guess, literally, by the end of the day.
So, I'm over here.
Oh, sorry, yeah.
So I was wondering, with the Shannon limits for channel coding, right? Various kinds of codes, like turbo codes, et cetera, are approaching the limits. But is the energy of computation, I'm not talking about reversible computing, but the energy is it approaching the VNL bounds now, or how far away is it relative to those bounds?
How far? It is actually pretty far in most cases. In fact, we are as sloppy in energy as we are with memory. So you remember that I studied programming where 16 kilobytes was pretty much, and I remember writing a kernel of basic sort of interpreter is 32 kilobytes, and nowadays anybody has a 1 gigabyte on it. The problem here that there's a great academic answer to this question, which is that in radio, for example, people argue we are very close in the wireless devices in transmission in the channel limit. that is true assuming that we have a Gaussian noise, which, as we know, holds and doesn't hold. So as a modeler, as my fellows, I'm always sort of very suspicious about this type of claims. In the computing, we are obviously, if you look at the chip design, we are obviously very far away from this energy limits, and so even in the next generations of Medfields and so on, we clearly see a lot of loss in energy still, and that's one of the reasons why the full computer power in a small scale is not yet that prevalent. But I mean, to be very honest, I do not know even a good quantitative thing. It depends on pretty much on the application domain and how well the assumptions hold when you do the math. Because we always know that by the end of the day, it's a math on a model.
Thank you.
We have time maybe for one last quick question.
Use two questions or two microphones?
One will do.
So this is a really futuristic kind of question, maybe. It has to do with allowed frequency bands. And let's forget about allowed. Forget all about controls. What would you imagine we might go to, not only for broadcasting, but for received power? So let's suppose we have a tuner for terahertz in this room, on board every person. And there's a terahertz transmitter with sufficient power, but not so much power, you're not going to hurt anything, but very precisely tuned for power or energy acquisition. And then on the other hand, let's suppose there's no limits on bands. We just don't think about regulations. We just think about what would be optimum. So you're a brilliant person, you must have visited this horizon. Could you comment?
Okay, yes, I visited this. I have much better people visiting this. This is what we call the cognitive radio. So the dynamic allocation of the spectrum, which is in fact inherently tied with the sensor radios, because if you do cognitive radio, it's simply the idea of looking and swapping dynamically the spectrum where you do not have signals occupying that spectrum space and then dynamically switching. So it's almost like having these different lanes and you switch the lanes, the typical traffic you see on 880 or 80 on that, except that every car is then bumper to bumper sort of going there. And that capacity, of course, that gives an enormous amount of capacity increase for our radios. Energy-related questions there are a little bit different. There becomes sensing energy question. You still need to make the decision or switch between the different spectrums. So you need tunable antenna energy that needs to be sort of taken into account. I was trying to look at that, but then I started to be so weak in my understanding that I decided that I will, one day when I have enough time, I will challenge my great radio guys to explain to me. I'm actually, if you talk about futuristic, I'm much more interested in one question which I have not a clear answer to yet. What's the sort of capacity of quantum entanglement computation, where you do the teleportation between the, teleportation in the sense that you have entangled particles and you do the information moving on that one. And that puzzles me much more than the cognitive radio. So my real futuristic thing, I'm actually interested in quantum entanglement communication, because that would be very, very nice for many other reasons. I think the energy and the problems come from the interference complexity, that you can't do many of those at the same time without somehow affecting the quantum states. But anyway, so.
All right, thank you very much for the wonderful talk, and please join me in thanking our speaker.
Thank you.